Welcome everyone to the first video in our AP Calculus BC series, where we try to cover the course as quickly, concisely, and clearly as possible. So the first concept you'll have to know is limits. In the CED given by the College Board says calculus uses limits to understand a model dynamic change. And it gives the example of average rate of change. So obviously, average rate of change is just the change in a function uh, over the change in the independent variable. Yet, if we want to examine this average rate of change, or by this definition, this rate of change at an instant, which we call the instantaneous rate of change, rate of change, then we're going to have big problems by this definition, because instantaneous means exactly at this point, and therefore we don't really have any good choices for A and B, and we'll have something like a 0 over 0, and this is clearly not helpful. And so limits is key for us to understand and interpret dynamic change, especially when it comes to instances like these, where we want things that are more about the instantaneous situation. Okay, so now we're going to move on to defining what a limit is. And we have two definitions here. One is the delta epsilon definition, which is the more rigorous or mathematical way of describing a limit. But this is not exactly tested. And what all you have to know is encompassed in the AP definition. So we're going to take a focus on this. Given a function f, the limit of f as x approaches c is a real number r if f of x can be made arbitrarily close to r by taking x sufficiently close to c. So let's consider this function f over here. And let's say I want to show that the limit as x approaches c of f of x is equal to r. And the way we show this is that we show that for any interval, so here we have for any interval around r, so we have here plus epsilon for some small epsilon and minus epsilon for some epsilon. For this y interval here, we can always find some interval close to c. So here we have c minus delta, right, and c plus delta, so that the values given by these function values falls within this y interval. So let me just reiterate that. So what we're trying to show is that however close we want to get to r, we can always achieve it with some interval close to c. So it's like, really, I'm just reiterating what it says here. So for any interval, however close we want to make to r, we can always find this neighborhood around c that satisfies falling within this y interval. So this is essentially what it's trying to say. Like the best way to experiment with this perhaps is you try to grab a function, something like this, and then you experiment with various different epsilon. So it's like you go like, can I go this far? And then you'll see if you can find an x interval where all the values fall within this given y interval, and you would keep doing it. So each time you're going to give yourself a y interval, and you're going to consider if there is an x neighborhood. So it's like for every y, this should work. So you can go larger, smaller, and all of them should work. And this is ultimately what constitutes a limit. Right. And just to draw attention again, this is the standard notation of a limit. It's also what's expected on exams. Limit, and then x to c below it, and then f of x equals a certain value. Right. Next, we get to the concept of one-sided limits. This is really easy to understand, way easier than the previous definitions. Single-sided limits are just limits when approached from one side. So if we have, as written here, limit of x to c plus, this denotes the limit of f as x approaches c from the right side. So for example, if we want to find the limit as x approaches 1 from the right-hand side, which is this limit over here, we would just consider, okay, I'm following f, and I'm getting closer and closer to 1 from the right side. And obviously, this approaches, as labeled here, -2. Sometimes you would have to estimate this. Our next video will cover that explicitly. Uh, on the other hand, of course, naturally, if you have a limit as x approaches c minus, then this just means approaching from the left. So if you have here, you follow f, and then you get to 4 when you hit x equals 1, right? So like you're getting closer and closer to this value. And notice how here the value itself of the function does not really matter. It's all about the trend. So for example, here, this open dot means that f is not actually equal to -2. It's equal to 4, which is the closed dot here. But the limit does not care. The limit does not care about the value itself. And this is really important to note. And we'll continue to emphasize this in the next videos. So the limit does not care about the value itself, as seen here. Then let's do one more example. The limit as x approaches 6, this is just a normal limit. You just consider both sides. Again, the value itself doesn't matter. On both sides, they agree to 5. Yeah. Here we have some more examples. This is just, again, really obvious. As it approaches -3, from the left-hand side, it becomes 6. And as it approaches from the positive side, it is 2. Okay, so now we're going to move on to vertical asymptotes. So previously, for example, in Algebra 2 or pre-calculus, there's this certain phenomenon where functions tend to grow unboundedly large or unboundedly small. And in calculus, we describe this phenomenon with vertical asymptotes. Basically, it's a way we choose to term positive infinity and negative infinity in terms of function value. So we say that x equals a, which is some vertical line, is a vertical asymptote of f if and only if we have the limit from the left-hand side or right-hand side tends to positive or negative infinity. So only one of these needs to hold true. So for example, if from the left-hand side I have positive infinity or negative infinity without the other one being true, it would still hold. So for example here, in this graph here, this is the classic 1 over x, and we have a vertical asymptote here at x equals 0. And this is because, as we'll show how to compute later, this is because the limit as x approaches 0 from the negative side is of 1 over x equals negative infinity, and from the positive side, it is positive infinity, right? So from the positive side, it goes all the way up to infinity. From the negative side, or like from the left-hand side, it goes to negative infinity. Okay, so another example here is this is a piecewise defined function. Piecewise defined functions appear quite often in AP exams. We'll show examples of them in our practice set session later. But here, at least, this piecewise function has a vertical asymptote at x equals 0 here again, where on the right-hand side, where on the right-hand side, limit as x approaches 0 from the positive side is equal to positive infinity. While from the negative side, we really don't have anything special. The limit from the left-hand side is just 0. But as long as one of them is true, we claim to have a vertical asymptote. Okay, and so final example here, we have the logarithm, log x, and this also has, coincidentally, all three, also has a vertical asymptote at x equals 0. Yeah. Okay, next we move on to horizontal asymptotes. The concept of a limit can be extended to include limits at infinity. And the way this works is just really simple. We consider what happens to this function as we take x to positive or negative infinity. And if this converges, or reaches some real number L that isn't infinity or it's bounded, then we have a horizontal asymptote of f. So here we actually have this really interesting logistic function. And if you just by observing the graph, one horizontal asymptote here would be y equals 1, because as it goes to positive infinity, it gets closer and closer to 1. On the other side, we see that the limit as x approaches negative infinity seems to be 0. So we have another one, which is y equals 0. So it is possible to have two horizontal asymptotes. It is possible to have one if only one of these is true, or if they're the same. Um, or you can have none. So for example, if I have y equals x, then there isn't a horizontal asymptote because as this function approaches positive or negative infinity, we're not reaching some bounded value of L. Lastly, we have the arctangent function. What's really nice about the arctangent value is that its range is negative pi over 2 to pi over 2. And really, you just consider what the arctangent function takes to be, or like what the tangent function takes to return a positive infinity value, which is just as you get closer and closer to a slope of positive infinity, you'll get to an angle of pi over 2. So therefore, one horizontal asymptote is y equals pi over 2 as x approaches positive infinity, whereas if you want to get as low of a slope as possible, then you're getting closer to negative pi over 2, which is what this part, this x tends to negative infinity does. So in the end here too, we have two horizontal asymptotes. And that covers everything for today's video. Thank you.